I want to prove that there are infinitely many primes. So I'm going to assume the opposite. I'm going to assume there are finite primes. And I'm going to say there's going to be n of them. So this is going to be a proof by contradiction, where you assume the opposite of what you want to prove. So I'm going to let P be the multiple of all the primes, all n of them, say, where P sub n is going to be the largest one. So P of n is the largest prime. And here we can say, okay, P1 is the smallest prime, P2 is the next smallest, etc. I'm going to consider P prime to be P plus 1. So I'm going to take my number P, add 1 to it. So that's going to be the product of all the prime numbers plus 1. So in other words, P prime is this. Okay. Notice this form is in the same form as the division algorithm. Okay. So the last number here, this 1, is the remainder. So if I take P prime and divide it by any prime number, P1, P2, whatever, I'm going to get a remainder of 1. So that means that P prime is not divisible by any prime number. So P, well, I'm going to write it Pi for all I. Okay, so for all prime numbers, all n of them, it's not divisible. Now if I use the fundamental theorem of arithmetic, what does that say? So the fundamental theorem of arithmetic says that any number, let's say greater than 1, can uniquely be presented in the form of a product of prime cofactors. Okay, so that means that, let's say for my number P prime, if I take P prime, I can write it in terms of a product of prime numbers. Let's say prime number A and prime number B. So just by the theorem. But what I showed here was I couldn't do it. P prime was not a product of prime numbers. Because if it was numbers, it would not have a remainder of 1. So you cannot represent P prime as a prime number. That's what we said over here. So there's a contradiction. The theorem says you can, but we showed it doesn't. So there's a contradiction there. So because there's a contradiction, we conclude there are infinite number of primes.